Hello there, students. So welcome back. And in today's lecture, we are going to continue in this current chapter talking about ionic and molecular bonding. In the previous lecture, we focused a lot on ionic compound, and in today's lecture, we're going to focus on the other half, which is on molecular compounds. And then we will end with talking about a new idea called electronegativity. To connect back to our previous lecture, remember that the driving force behind bonding in molecules is that atoms need to fulfill a rule called the octet rule, which means they must have 8 electrons on their valence shell, or the duet rule for hydrogen and helium, meaning they have 2 electrons on their valence shell. And remember that the reason for this is that atoms will always want to have the same valence electron configuration as that of the nearest noble gas, because every noble gas will have a full shell of electrons, which gives it a special stabilization that all atoms want. And so if you are not a noble gas atom with that full shell of electrons, you must interact with other atoms, resulting in what is called as a bond. In the previous case, we saw that you can achieve this by giving and taking electrons, resulting in something called an ionic compound, where the atoms are attracted to each other by an ionic bond. And this occurs when you have a metal and a nonmetal. A metal is an atom that likes to give away its electron, whereas a nonmetal is an atom that likes to take away electrons from others. So it's a perfect pair. What happens though if you have two nonmetals together? For example, if you have 2 chlorine atoms, both of them will have 7 valence electrons only, and both of them will need one more. So chlorine is not going to take 1 electron from the other chlorine and making itself happy, while the other chlorine is now 2 away from a full valence electrons, right? So in this situation, you can give and you can take, but what you can do is share electrons to make a bond, what is known as a covalent bond. And this is what we will focus on today's lecture. Here are some more examples. Let's say you have 2 hydrogen atoms, and as you know, hydrogen is element number 1, so it has 1 electron. It needs 2 electrons to fulfill its first shell of electrons. So if you are a non-metal like hydrogen and there are no metals around to give you that full shell of electrons, so you come together closer and closer, putting those electrons that each of you have in between you two. They are being shared by both hydrogens. So from the perspective of the left hydrogen, he would see that he has 2 electrons, a full shell of electrons. And from the perspective of the right side hydrogen, he also sees that he has 2 hydrogens, a full shell of electrons. And because of this, this molecule is more stable than the 2 hydrogens independent of each other. And because it is more stable, they prefer this state and they form a bond. We can signify the bond between the hydrogens with those 2 electrons represented with a line in this Lewis structure drawing. And in fact, this sharing of electrons occurs with many other combinations of nonmetals. For example, here, if you have again a hydrogen, it needs 1 more electron to fulfill its duet rule, and you have chlorine, which has 7 electrons, so it needs 1 more electron to fulfill its octet rule. So what happens is, again, there will be no giving or taking in this case, but there will be a sharing of electrons, with 1 electron coming from hydrogen and 1 electron coming from chlorine. Again, in this arrangement, you can see that hydrogen has 2 valence electrons, and at the same time, chlorine has 8 valence electrons, duet and octet. Again, we can represent this bonding with a line that connects hydrogen with chlorine. These are 2 examples of what we call Lewis structures, and in a Lewis structure, we only care about valence electrons. Notice that chlorine has 17 electrons, but we don't draw all 17. We only depict the valence electrons in chlorine. In Lewis structures, a single line represents a pair of bonding electrons, whereas 2 dots represents a pair of non-bonding electrons. So for example, in this case, chlorine has 1, 2, 3, 4, 5, 6 electrons are not involved in the bonding. You can consider these electrons solely belonging to chlorine, whereas that line between hydrogen and chlorine represents a pair of 2 electrons that are shared between hydrogen and chlorine. Let's have some more practice with drawing Lewis dot structures of molecular compounds. From a conceptual perspective, you can draw these 2 atoms of fluorine separately with their valence shell of electrons. Remember, fluorine belongs in group 7A, so it has 7 valence electrons. So you can depict those 7 valence electrons as dots around fluorine. And you can also imagine that each fluorine will have one electron that will be shared between the two of them. Each fluorine will contribute one electron in that bonding pair. And you can depict that pair of bonding electron right in between the two atoms. Again, we call that pair of electron a bonding pair, and the other pairs are called the lone pairs. They are not involved in bonding. And again, a pair of electron means two electrons. And to simplify this structure, every time you have a bonding pair of electron, we want to draw a line that connects the two atoms. So we use this Lewis structure to represent this molecule of fluorine. Let's try another example. This is CH4. It is known commonly as methane. It is a molecular compound that is composed of a carbon and 4 hydrogens. The Lewis dot structure of carbon has 4 electrons around it because carbon is in group 4A, whereas hydrogen has 1 electron because it is in group 1A. From this, we can see that carbon needs 4 more electrons to be an octet, while hydrogen needs 1 more electron to be a duet. So for this bonding to occur, each of the hydrogen will make a bond with the carbon. So carbon will make 4 bonds. As seen from this depiction, you can see that there are 8 electrons surrounding carbon, and you can see that for every hydrogen, it is close to 2 electrons. So every atom in this molecule is happy with an octet or a duet. Again, those bonding pairs of electron can be depicted with a line connecting the atoms from which the electrons are being shared. So in this slide, I was trying to give you a conceptual understanding how bonding occurs in molecular compounds. Now, Lewis structures can get very complicated, so we will need a more systematic way in drawing them. In drawing any Lewis structures, you can follow these 4 steps. First, you have to determine the arrangement of the atoms, how they are connected to each other. Then you need to determine what is the total number of valence electrons contributing from those atoms, making sure that you do not have more or less valence electrons than you started out with from the individual atoms. Then the next step involves bonding the atoms together, and in this step you have to figure out what is a central atom. And lastly, in step 4, you put the remaining electrons around each atom, making sure each will have an octet. And if an octet is not achieved, you might have to make the lone pairs become bonding pairs, and resulting in something called double or triple bonds. Let's see how you can use this guideline to help you draw the Lewis structure for carbon dioxide, CO2. Again, step 1 says to determine the arrangement of the atoms. And most of the time, this simply means which atom is your central atom, the atom that the other atoms are connected to. There are 2 things you can use to determine what is your central atom. The first is symmetry. So for example, in this case, you have 1 carbon and 2 oxygens. How would you arrange this molecule to provide symmetry? Would you put the carbon in the middle, flanking it with 2 oxygens on the outside, or 1 oxygen in the middle, flanking on one side carbon and one side oxygen? You would put the carbon in the middle because that will give you a symmetry within this molecule. Another guideline that could help you to determine this is that you want to put the least electronegative atom in the center. This idea of electronegativity will be covered in the second part of this lecture, so for now, let me tell you that carbon is the least electronegative atom between carbon and oxygen. Once you have determined the connectivity of the atoms, in step 2, you need to count the total valence electrons. You say to yourself, I have a carbon. Carbon belongs to group 4A, which means it has 4 valence electrons. So if I have only 1 carbon contributing 4 electrons each, that gives me 4 electrons. Then you move on to the next atom. You say to yourself, I have oxygen. Oxygen is from group 6A, so it has 6 valence electrons. I have 2 oxygens, so 2 times 6 is 12. So from the oxygens, I have 12 electrons. That's all the element I have, so I add them to give me a total of 16 valence electrons. This is the number of valence electrons you should always make sure you have at the end. You do not want to have more or less than this. Okay, step 3. Step 3 says to connect the atoms together. Remember that we have already determined that the connection is going to be oxygen to carbon to oxygen. So now we just have to connect them. And remember that this line just means that there are electrons being shared between those 2 atoms. Step 4. Step 4 is the most challenging step, and it might require the most work. Step 4 says you have to place the remaining electrons around the atoms to complete the octet. it is best to start putting electrons around the non-central atom. So in this case, the central atom is carbon. So I would start putting electrons around the oxygen. Remember from step 2 how many electrons we have. We have 16 electrons, and we have already used 4 electrons. Right? 2, 4. So this is our 6, 8, 10, 12, 14, 16. Voila! We have used all of our valence electrons. So now we need to make sure that each atom has a full octet. Counting electrons around oxygen, we see that each oxygen has 8 valence electrons, whereas that carbon has only 4 electrons. 2 electrons here and 2 electrons here, making that 4 electrons around carbon. So carbon does not have an octet. So I like to say that this structure is not happy. And since carbon does not have a full octet, he would like to share electrons to achieve that full octet. And so carbon will look to his neighbors and ask to share electrons. And remember that when electrons are being shared, they are not taken. So for example, if I share this pair of electrons between this oxygen and this carbon, oxygen will still have its 8 valence electrons. And it doesn't matter which pair of electron you take, it's just a representation. After we do that, we can see that now carbon is getting happier. It has 6 valence electrons, but not yet 8 electrons. So you can continue to share further. And for the sake of symmetry, I'm not going to ask this pair of electrons to move in from the same oxygen again. I'm going to look to the other side, since we haven't shared anything from this oxygen. We can now ask this oxygen to donate its pair of electron in. So when that oxygen donates its electron in, that carbon now will have a full octet. When each atom has a full octet, you know that you have your complete Lewis structure. This kind of looks messy, so at this point we would want to redraw our Lewis structure. Every bonding electron should be represented with a line. So in this case, since there are 4 electrons or 2 pairs of bonding electrons between the oxygen and the carbon, we can draw it as 2 lines instead. That is called a double bond. Let's do another example with hydrocyanic acid, or HCN. Again, first step is to consider what is the center atom. For sure, hydrogen will not be your center atom because hydrogen can only make one bond. If you can only make one bond, you can't be the center atom because a central atom will have to make bonds with all the other atoms. So now you're left with either deciding carbon is the center or nitrogen is in the center. So if you know that carbon is less electronegative than nitrogen, then you will be able to decide that carbon will be your central atom. Like I said, I will have to give this to you since we haven't learned about electronegativity. Step 2. Let's count how many valence electrons you have from this molecule. Hydrogen will give you 1, carbon will give you 4, and nitrogen will give you 5, giving you a total of 10 valence electrons. Connecting the atoms that we know with a bond, we see that we have used up 4 of our valence electrons. We only have 6 valence electrons left. And the next step, step 4, is to put in the rest of the electrons first around the outside atoms. In this case, that's nitrogen. So we put 2, 4, 6, giving us a total of 10 electrons. So we have used all of our valence electrons. Do we have a full octet for everybody? So hydrogen's happy, it has a duet. Nitrogen is happy, it has 8 electrons. But carbon, again, has only 4 electrons. Again, carbon needs to share electrons, so it looks around its neighbor and see where electrons can be shared. Hydrogen has no more electrons to share, so your only option is to share electrons from nitrogen. How many electrons for nitrogen would you need to be happy? You would need 4 more electrons, because you only have 4 electrons as it is right now. So to do that, we move 2 additional pair of electrons to be between carbon and nitrogen. Hydrogen still has 2 electrons, so duet is good. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 electrons, so it has an octet. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Also an octet, so everybody's happy. Again, there are 6 electrons between carbon and nitrogen, or 3 pairs of bonding electrons between carbon and nitrogen. So we can represent those 3 pairs of bonding electron again as lines, this time 3 lines representing a triple bond. So now you are exposed to single bonds, double bonds, and triple bonds. Those are the 3 types of bonds you will see in this class. Notice in this case how many bonds are connected to carbon. 1, 2, 3, 4 total. In this case, how many bonds connected to carbon? 1, 2, 3, 4. In this case, how many bonds connected to carbon? 1, 2, 3, 4. That is not a coincidence. Since carbon is in group 4A, has 4 valence electrons, so it needs 4 more electrons to fulfill its octet. In order to fulfill its octet, it needs to share 4 electrons from others, so it will form 4 bonds. This is a pattern you will see in covalent bonding. Silicon below carbon is also in group 4A, so it will also have 4 bonds. Nitrogen, as in the previous example that we just saw, has 1, 2, 3 bonds. Nitrogen will always have 3 bonds. Again, because it is in group 5A, it has 5 valence electrons, so it needs 3 more electrons to be an octet. In order to obtain those 3 electrons, it will have to share, making 3 bonds. Phosphorus in the same group will also make 3 bonds. Whereas you move to 6A groups, oxygen and sulfur, they will always make 2 bonds. Moving on to the halogens, 7A group, they will always make 1 bond. The same is true for hydrogen, which needs that duet, so it will need 1 more electron, making 1 bond. Now here's an exception. Boron in group 3A will always make 3 bonds. Now 3 times 2 electrons each in those bonds give you 6 electrons. So it turns out there are some elements that does not have to follow the octet rule all the time. So boron will have 6 valence electrons and it will be happy. And there are actually other elements that will have more than 8 electrons and it will be happy too. And the reason for that exception is beyond the scope of this class. So in this class, we just need to follow that every atom will either follow the duet or the octet rule. And when they follow those rules, you can always count on carbon having 4 bonds, nitrogen having 3 bonds, oxygen having 2 bonds, halogens having 1 bond, so on and so forth. So that's how you draw Lewis structures to represent the bonding in molecular compounds. Probably will need a lot of work to get the hang of this, and we will do a lot of practice in class. Now let's take a look at how we name molecular compounds. And I put in the parentheses here, simple molecular compounds, because molecular compounds can get very complicated. We won't get into that, not at least until the last chapter when we talk about organic chemistry a little bit. So for now, a simple molecule will look like this. You have 1 carbon and 1 oxygen. First off, you have to recognize this is going to be a molecular compound because both atoms are nonmetals. To start naming them, you put a prefix, and a prefix tells you how many atoms of that element is in that compound. And in order to do that, you need to know the prefix table, where if you want to say there's 1 of something, you say mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. So go ahead and make flashcards to memorize this table. Alright, let's go back into naming. In the parentheses, it says, if not mono. So if you start a name of a compound and the prefix is going to be mono, you can drop it. You do not have to include it. You only need mono if that prefix is somewhere in the middle of the name, as you will see. In this case, there's only 1 carbon, so that's going to be mono, so we can ignore it. Going on to the next part is you put the name of the first nonmetal. In this case, that's carbon. Now you put the prefix for the next element. For oxygen, there's 1 oxygen, so you can say mono. Then you can put the base name of the second nonmetal. So the base name of oxygen, remember, was ox. So that's going to be monox. And then you're going to add I, just like in ionic compounds. So that's going to be carbon monoxide. Notice it's not carbon monoxide. When your prefix has 2 syllables for oxygen, the last letter will be dropped out. This is something that chemists have just agreed upon. Let's try this one. So you have 1 carbon and 2 oxygens, and that carbon is in the front, so it won't have a prefix since its prefix would have been mono. And that oxygen, there's 2, so it's going to be di. So what do you think it's going to be? Carbon dioxide. Yep. Alright, what about this guy? You got P4S3. So you have 4 phosphorus and 3 sulfurs. Since we have 4 phosphorus and not just 1, we would say it's tetra for 4. Tetra phosphorus. 3 of sulfur, so that's trisulfide. The molecule's name is tetraphosphorus trisulfide. Fun, isn't it? All right, here's your checkpoint. Identify the following compound as ionic or molecular and write its correct name. This is NO2. You notice that the two atoms are nonmetals, so it's going to be molecular. So you have to follow nomenclature for molecular compound. And by the way, nomenclature is just another word for a system of naming things. So you got 1 nitrogen and 2 oxygen, so that's going to be nitrogen dioxide. Yay! That's right. Another checkpoint. Identify the following compound again as ionic or molecular, and then write its correct name. You got Na3N. Okay, you should recognize that you have a metal, sodium, and a non-metal, nitride, so it's going to be ionic. So now you have to think about the nomenclature for ionic compound. Remember, in ionic compound, you simply say the name of the metal and then the base name of the nonmetal with "ide" at the end. So in this case, this will be sodium nitride. Answer is D. Very good. Now let's do the reverse. The reverse is a lot easier actually for molecular compounds. If I give you the name of the compound, can you write the molecular formula? And in order to do this, you just simply translate in order the name. And the name is quite explicit, right? For example, it says diboron trioxide. Di meaning 2 and tri meaning 3. So that's B2O3. How about iodine pentafluoride? So I don't have a prefix on iodine, meaning it has only 1. And then pentafluoride, penta meaning 5, fluoride is a fluorine, so that's IF5. Yay, I told you that was easy. Before we go on to the next topic, let's have a review. Which element has the closest distance between its nucleus and its valence electrons? Another way of asking this is, which is the smallest element? So good if you said the smallest element was fluorine, because it is most to the right and most to the top, therefore it is the smallest element. Now, knowing the size of the element will help you tremendously in thinking about electronegativity, because they are very related. And electronegativity can be defined as the ability to attract shared electrons to itself. So if you think about the size and electronegativity, the smaller your atom is, the closer your nucleus is to that shared valence electron. So if your positive charge is closer to that shared electron, you will have a stronger attraction to it, so you will attract it much more to your side. Whereas if you are a large atom, your nucleus is very far away from that valence electrons. Your nucleus will have to go through many layers of negatively charged electrons before it even sees that last valence electron to attract it to itself. So because of that, fluorine is your most electronegative atom. It is your smallest atom. Now this is a table that gives you the electronegativity values and is empirically determined. It was measured in the laboratory. Another trend in electronegativity that you may notice is that nonmetals will tend to have higher electronegativity values, whereas metals will have very low electronegativity values. Remember that metals like to give away its electron, so therefore it doesn't have that strong of an attraction to the electrons in a bond. So what does this electronegativity have to do with anything? Let's go back to this first image that we saw earlier. Looking back at the bond between hydrogen and hydrogen, since they are identical to each other, the electrons that they share between them are shared very equally, 50-50 you could say, because they are identical to each other. Imagine if there was a tug of war and there were two people with the same strength, and if they were pulling to get those electrons, neither of them will have the electrons more to its side. So we say that there are equal sharing of electrons, and we call this bond not only covalent bond, but it is a non-polar covalent bond. Whereas on the right-hand side, the bond between hydrogen and chlorine, that's categorized as an unequal sharing of electrons. So that covalent bond is called a polar covalent bond. Again, you can go back to the previous slide to see that chlorine has a greater electronegativity value than hydrogen, so it can pull electrons to itself better. To annotate that electrons aren't shared equally in this bond, we can put a sign that is a Greek letter delta, meaning partial, and negative, meaning that this chlorine is partially negative, whereas this hydrogen has a delta positive, meaning partially positive, and hydrogen has a partially positive charge on itself because electrons are being pulled this way. With this layer of electronegativity to understand bonding, let's add another definition to ionic bonds that we covered in last lecture. Remember that we said that ionic bond occurs between a metal and a non-metal and is a result of electrons transfer. And in terms of electronegativity, it also has a large electronegativity difference of 1.8 or more. So if you take the difference between two atoms' electronegativity values, if it is greater than 1.8, then it is ionic bond. So for example, if you take a look back at that chart, the difference in electronegativity between chlorine and potassium is 2.2. And the difference is always going to be an absolute value. You just take the larger value, subtract it from the lesser value. Let's do some more examples. You have nitrogen and sodium. What would its electronegativity difference be? 2.1. What about sulfur and cesium? 1.8. You can see that all of these are greater than 1.8 and that they are difference between a metal and a non-metal. Both of these definitions will fit ionic bond. Whereas in this lecture, we're talking about the opposite of ionic bond, the covalent bond. But again, I said there are two types of covalent bond, polar and non-polar. So let's talk about the polar one first. From that first slide, we saw HCl bonding. And if you take their difference in electronegativity, delta En, you will see that it's 0.9. It's less than 1.8. What about carbon and oxygen, another two nonmetals? It's 1.0. What about nitrogen and oxygen? 0.5. So it turns out if you have an electronegativity difference of 0.5 to 1.8, you are considered polar covalent bond. So from the previous slide, we saw that ionic bonds result from an atom pulling electrons totally to itself, where the difference of electronegativity is greater than 1.8. So if it pulls electrons to itself so successfully, you can imagine that one side is a full negative charge and one side is a full positive charge. Comparing that to a polar covalent bond, we know that the electrons are still being shared and not pulled completely to one side. We can again call that being partially negative on one side and partially positive on the other side. So in this kind of drawing here, we can see that most of the electron, which is purple, is on one side, but still this side is not completely devoid of that purple electron shading. Contrast that to a nonpolar covalent bond. In a nonpolar covalent bond, your electronegativity difference will be 0.4 or less. So for example, if you are a bond between identical atoms, nitrogen and nitrogen in this case, you will have 0 as your electronegativity difference. Even if you are different elements, you can also still be nonpolar if your electronegativity difference is equal to or less than 0.4. So for example, in this case, the difference in electronegativity of hydrogen and carbon is 0.4, so it is still considered a nonpolar covalent bond. So you can depict that with electron density being shared equally among the two atoms. Let's summarize it. If your difference is between 0 and 0.4, you are considered nonpolar. And if your difference is between 0.4 and 1.8, you are polar. And if your difference is greater than 1.8, you are ionic. Now actually, I don't like to use this chart very much because I like for students to have a more fluid understanding. So I want you to be able to predict whether something is polar, nonpolar, or ionic just based on the periodic table itself. And to help you do that, you should memorize this fact that carbon and hydrogen is always going to be nonpolar. Remember, because their difference in electronegativity is 0.4. Anything other than that, you can use logic to reason. For example, if I give you two elements and one is a metal and one is a nonmetal, you will automatically say that's going to be ionic. You don't have to calculate delta En to know that fact. Or if I give you two elements that are nonmetal, like say oxygen and fluorine, you do not have to know the electronegativity values to tell me that's going to be a polar bond. You just know that fluorine is going to be more electronegative than oxygen because electronegativity increased from left to right. Same thing, if I give you oxygen and sulfur, you know that oxygen is more electronegative than sulfur, so you can draw a bond where oxygen will be partially negative. Now there are trickier cases where you would need the electronegativity value, but again, in this class I won't ask you those cases, And if I do, you can always answer it using the trends in electronegativity instead of electronegativity values when electronegativity values are not explicitly given to you. And when you have a polar covalent bond, you can depict that with a dipole arrow. A dipole is a separation of charges in a polar bond. You can think of dipole as just like the positive and negative side of a magnet. So for example, the bond between carbon and oxygen, you can designate again that oxygen is a little bit more electronegative, so it is partially negative, delta negative, whereas carbon is partially positive, that delta sign with the positive sign on top of it. You can draw a dipole, and a dipole sign always points to the more electronegative end, and that end has an arrow, whereas the opposite end will have something that resembles a positive sign. Let's see some more of these examples. Oxygen is more electronegative than nitrogen, so oxygen will be partially negative, so the dipole can be drawn towards the oxygen side. It doesn't matter where you draw this dipole sign, but most of the time you will see me drawing it on top of the bond. You can also draw dipoles in molecules. And when you draw dipoles in molecule, you want to draw it for each bond. So for in this case, hydrogen and carbon has no dipole because their electronegativity difference is 0.4, so it is nonpolar. Whereas carbon and nitrogen will be more electronegative than carbon. So we would draw a dipole towards nitrogen. Yay, checkpoint! Without looking up the electronegativity values, which of the following bond is considered a polar covalent bond? So let's do process of elimination. You want polar covalent. Polar covalent means that they have a large enough difference in electronegativity values. So you can cancel out sodium and fluorine because one's a metal, one is a nonmetal, so that's actually ionic. So now we have carbon, fluorine, carbon, 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 hydrogen. You can now cancel out C because carbon and carbon are identical to each other. And then lastly, you can cancel out D. Carbon and hydrogen have an electronegativity of 0.4, so that's going to be nonpolar covalent. So your last answer is going to be B, CF. So in this lesson, we talked about how to write the correct name given the formula of a molecular compound, or given the name of a molecular compound, writing its formula. We also delved into drawing Lewis structures for these molecular compounds and using electronegativity to determine the polarity of a bond. This may seem like a short lecture, but there is a lot actually to go through, so I will see you in class for more practice.